We will discuss when and why an electric charge moves in a circular path under the influence of a magnetic field. We will derive the equation for the radius of the path and then we will answer a simple problem based on this. Consider a particle having electric charge Q. It is moving with velocity v and experiences a magnetic field B. Then the magnetic force on the particle is given by Q into V cross B. So we take the cross product of velocity vector and magnetic field vector and multiply this with the electric charge. As happens with cross product of vectors, the magnetic force is perpendicular to both velocity and magnetic field. Consider a particle of mass m having electric charge q and moving with velocity v. Suppose that there is a magnetic field B perpendicularly into the plane of the figure. So you can see that the magnetic field vector is perpendicular to the velocity vector. Now, if you want, you can also assume that the magnetic field is perpendicular out of the plane of the figure. The only thing you need to make sure is that the magnetic field is perpendicular to velocity. The angle theta between velocity and magnetic field is 90 degree. So the magnitude of the magnetic force on the particle is qvb sin theta. Since sin theta is 90 degree, so the magnitude of the magnetic force is qvb. As you can notice, when I am writing a vector without arrow symbol, this means I am taking its magnitude. As we saw, the magnetic force is perpendicular to velocity. Therefore, the particle moves in a circular path and here the magnetic force does the job of centripetal force. Centripetal force equals m into v square divided by r. Therefore, the magnitude of the magnetic force is m into v square divided by r. We found that the magnitude of the magnetic force in this scenario is qvb. So qvb equals m into v square divided by r. Divide both sides by v. Q into b equals m into v divided by r, and from this we find r equals mv divided by qb. So this is how we find an expression for the radius of the circular path. See the diagram. See the directions of velocity and magnetic field, and also see the direction of magnetic force. From the direction of velocity and magnetic field, you can find the direction of magnetic force by using the definition of how cross product works. As you can see, in this diagram, I have assumed that the electric charge is positive, and if the electric charge is negative, but velocity and magnetic field remain in the same directions as in this diagram, then the magnetic force will be on the other side. We will see a problem based on this. This problem came in a previous year exam paper of CBSE class 12th physics. A particle of mass m and charge q describes a circular path of radius r in a magnetic field. If its mass and charge were 2m and q by 2 respectively, then what would be the radius of its path? This is how we solve. If the speed is v and magnetic field is b, then the formula we use is r equals mv divided by qb. To find the new radius, we multiply the old radius by the factor by which the radius will change. To find the factor by which the radius will change, in the formula of radius, for each variable, we write the factor by which the variable changes. If a variable does not change, then write 1. In place of m, we write 2 because mass changes by a factor of 2. In place of q, we write half because the electric charge changes by a factor of half. And in place of v and b, we write 1 because speed and magnetic field are not changing. We simplify and find that the answer is new radius equals 4r.